Okay, I hope you had a good weekend, and it has been a while since our last lecture. Let's have a brief review of the three very important theorems we learned for the congruence of two triangles. First one, side angle side theorem. I'll start with Aaron. Could you tell me what this theorem is about? Side angle side.
It's basically proving some congruence between two triangles with the proof of two sides and an angle.
Are there requirements about the two sides?
Huh?
Any requirement about the relationship between the two sides?
You need proofs.
Okay. For example, could I pick this side, this side, this side, this side, and this angle?
No.
Okay.
You don't have a matching side on the third one.
Okay. So in particular, here we emphasize the angle must be between the two sides we are comparing. Okay. So first pair, second pair, then the angle must be the one between them. We cannot pick a third pair. If we pick this angle, then it's not a side angle side theorem. Amy, can you tell me what this theorem is about?
So if all the sides are the same length, then the two triangles are congruent.
Okay, so if we have first pair, second pair, and third pair. If this pair of sides same length, this pair of sides same length, this pair of sides same length, then the two triangles are congruent. Let's use congruence. And the last one. Fred, the last one. Angle, side, angle.
Yeah.
Can you tell us what this theorem tells us?
Like one side and with two angles, that's angles, near with the side set angle.
So if we pick this pair of sides, the two angles must be connected to it. First pair, second pair. If we have this angle side angle, angle side angle, then we have the congruence of the two triangles. Okay, three very important theorems, and we will use this repeatedly. Another useful fact, we observed that Kira, can you hear us, Kira?
Yeah.
Okay, turn on the camera. Okay, cool. If we consider a triangle ABC, then the following two conditions are equivalent. Equal angle equal sides is equivalent equal angle. Okay, a very useful property. So we call such triangles isosceles triangles. And another theorem that's highly not trivial, not about equality, but about inequality. Give it an arbitrary triangle. Oh, that's too special. Let me make it more. Okay. So if the length of a is equivalent to the corresponding angle, edge BC. The opposite angle is angle A. Edge AC, the opposite angle is angle B. Okay. So longer side, larger angles. Shorter side, smaller angles. In particular, we can formulate the following. Is AC AB is the same as okay, let's pause for a few seconds to recall how we proved this statement. Why are they equivalent? Did we prove this in one step or in two steps? Jessica, what do you think? Do you remember the proofs? Uh-huh. Okay. And Kira? Okay. So we proved this in two steps. The first step, which is that longer sides imply larger angles. For this, because this is longer, we can construct a piece with equal length. Then we can use the previous information to get the inequality. The second direction, larger angles to longer side, we use proof by contradiction. So two different proofs. This direction, direct proof. But the other direction, proof by contraposition. Okay. We prove that longer sides imply bigger angles, and for bigger angles imply longer sides. Therefore, the two conditions are equivalent. Okay. So a very useful theorem. How useful it is, it can be used to prove a very useful inequality. It's called triangle inequality. Suppose we have a triangle. Then the summation of the length of two sides is always longer than the length of the third side. You can see AB. Okay. Let me check with Amy. Did we prove this last time?
I don't think so.
All right, okay. Let me check the notes. So lecture 8. See where we stopped. Okay, wait. Okay. So now it's easy to check. So that's the last step we had. First one, longer side, bigger angles. So we said this, we want to prove this, the corresponding angle is bigger than this one. Because this side is longer, we can find a point such that this side has the same length. Then the two angles are the same. However, angle A is bigger than this because it's part of it. And angle B is smaller than this one because it's the exterior angle of the triangle ABD. So angle A bigger than CAD. CAD is the same as CDA, which is bigger than angle B. So longer side, bigger angles. The other way will be proved by contraposition. We want to prove that bigger angles, longer side. So we show that the opposite of this, the negation of this implies the negation of the condition. Okay, so that's the last theorem we have last time. So we can go back to give it our application. Okay, let's see why is this. Why the summation of the two sides will always bigger than the third side. To prove this, we will do an extension. We will extend AC. To where? With the same length as AB. So this is about, okay. Okay, so we extend segment to a line, and we pick a segment on this line with equal length. Then we connect this, we get a triangle. Let's consider the triangle ABD. In this triangle, AD and AB are the same. So equal sides, equal angles. Equal sides, equal angles. Now let's compare the angle. And C. Angle CBD. Let's compare this CBD to be this angle. Go BDC to be this angle. I wanted to claim this is bigger. Can you tell me why? Why this? Well, we can see on the graph it is bigger, but how do we justify our claim? Aaron, what do you think?
Well, CBD and BDC are somewhat the same thing, to be honest. So therefore, let's see, they're basically part of the same shape themselves. So I would say they're equal.
Okay, you claim these two are actually equal.
Well, yeah, they're part of the same shape.
Okay, let's check. Okay, so here I should write. So why? Because angle CBD is bigger than angle ABD. Aaron, do you agree with this statement? CBD, ABD.
Yeah.
Okay, because this is just a part of the bigger angle, therefore it's bigger. And ABD, ADB, they are the same. ADB is the same as CDB. Okay. In this way, we proved that this angle is bigger than this angle. Now we will apply our previous proposition. Bigger angles, longer sides. a bigger angle, longer side. Smaller angle, CDB, shorter side. And then C and D is the summation of AC with AD. And by our construction, AD has the same length as AB. Therefore, we have the summation of the two sides is bigger than the third side. This is the triangle inequality. We finish the proof. We used the theorem we just approved that bigger angles, longer sides in a triangle. Okay. This is only true for triangles. If we go to quadrilateral or with more edges, it's not true. Okay, now next, let's consider another application of this triangle inequality. Let's consider 2 points. Two and three. Five and two. Okay, let me check with Jessica. What's the shortest path from one point A to B? What's the shortest path? How do you move quickly from A to B?
You just draw a line from it.
Okay, we draw the line segment from A to B. This is the short path. Now let's go a little bit requirement. We have to drop off. When we're moving A to B, we have to drop off something at the x-axis. Okay, additional requirement. Okay, so without this requirement, we can go straight from A to B. But now we have the requirement, we have to reach the x-axis before we make the turn and to B. Okay. Amy, what would you do if we want to go from A to B while get to the x-axis?
You would, for x, you would add 3.
So what path? What path would you pick?
I don't know.
You don't have to be optimal, any path.
I would just like go that way.
Okay, so one way, let me check. So one way we can go, okay, we want to reach x-axis, let's satisfy this first. We go to directly to the x-axis. Now we satisfy the requirement, we turn our head, we move towards B.
Oh, because at first I thought you meant like just directly go to B.
Okay, so that's the previous case. Now we have an additional requirement. Okay, let's continue. Fred, what would you do? Oh, Fred just left. Okay, Kira, what would you do?
Would it be shorter if you went all the way to like 5 and then went up to B?
Okay, so a second choice, we go all the way to 5, then I go to B. Jessica, what would you do?
Wait, could you repeat the question? I couldn't hear it.
Okay, so how could we move from A to B while reach the x-axis?
You could go down to 2 and then to B.
Okay, that's one choice. Other choices.
You could go to 5 and then to B.
Okay, that's the second one. So that's our first choice. Second choice, let me use a different color. And Fred, third choice.
His choice. Is it additional?
Additional requirement.
Okay. Additional requirement.
So when we move
Wait.
from A to B, we must reach the x-axis. Maybe Aaron. A third path, different from this two.
Wait, so we must reach the x-axis, right?
Yes.
Maybe A go to 4 and then to B.
Okay. Okay. I will have a different choice. We go to 4, then we go to B. Kira, another different one.
You could go to 3.
Okay, we can also go to 3.
You can technically also go to 1. If you want to go.
Okay, creative, that's nice. Let's go to 1, have a different color. I can even go to 1. Then I turn back, go to B. Okay, so we have many choices. Which one is the shortest?
Probably not the one where you go to 1.
Okay, okay, get rid of that one. Which one is shortest? Of all possible paths.
I say 3.
Okay. Press move A to 4. Okay, that's Aaron. Okay. So we can guess, but even if we found a shortest path, how do you argue it's the shortest?
Count how much points it goes through.
Okay, so let me give you another argument. What we do is we are going to find the reflection of B about the x-axis, the mirror point. If this is the mirror, what's the image of B? Aaron?
A.
Okay, let's think. If this is a mirror,
Yeah.
B sit over here, look at the mirror, see where his image is. It be behind the mirror, right? Inside the mirror. Okay, Kira, does what I say make sense? Okay.
Yeah.
Okay, so what's the image of B?
Like
this will-
-2, like
Okay.
5 -2.
Okay, so the image will be at. Let me extend this a little bit.
Oh, I didn't understand that.
Okay, yes, that's okay. So sometimes description is not that concrete.
Oh, I
Okay.
see.
Missed a little bit. Let's get back to this. Okay, this will be the image of B. Let's put a hat on top of it. Then I will connect A with the image of B. Okay, then I connect. Let me make further connections. Oops, sorry. Wrong choice. Okay, now let's check. I claim if we go from A to this point, then back to B, so the total length is the same as we go from A to the image. Do you agree with this? So I first find the image, then I connect the 2 points. So this is a straight line.
That's gonna make a triangle.
Okay, so because if we look at these 2 triangles, they are congruent. So these 2 sides, same length. The 2 sides, same length. In particular, if we denote this as point T, we know that segment Okay, now let's check if we pick a different point. For easy comparison, I'm going to pick the first path. If we first go from A to E, then E to B, the total length will be AE. E, B. Okay. And because B is the image, I claim A, E, E, B, image. Okay, so these two passes from E to B or to its image have the same length. Okay, think about why. Okay, we can use different theorems. We can use Pythagorean theorems because the square of this is the summation of these two squares, which is the same as the summation of these two squares, which will be the square of EB. We have different proofs. Now let's compare the summation of this A, E, and EB hat with AB hat. Which is longer, which is shorter? And okay, why? Amy, which one is longer, which is shorter, Amy?
The first one is shorter.
Why?
Because it's like just, I don't know, it's just more simple.
Okay. So because we can look at the triangle A, E, and the B hat. If we look at this triangle, we know that the summation of the two sides is longer than the third side. This is the third side. This is the summation of the two sides. It's the theorem, our previous theorem, the triangle inequality. For whatever triangle we have, the summation of two sides is always bigger than the third side. Same thing here. If we look at the triangle A, E, B hat, then the summation of the two sides always longer than the third side. Third side, summation of two sides. So by our previous triangle inequality, we know so wherever we stop on the x-axis, we have a triangle, and this will be shorter than the summation of the two. In particular, so A, B hat, this path give us the shortest path. So the conclusion from here is, if we want to find the shortest path with a stop on this x-axis, we need to find the image point about this, and we connect the two points with the segment. So the conclusion is this gives us the shortest path. Okay, any question about this one? Let's think about this. Let's have 5 minutes break. Think about the proof, and we will ask for questions after the break. We'll be back at 8:17.
Okay.
Okay, 5 minutes break. Any questions about this argument? How do we find the shortest path? Aaron, any questions? It's okay?
Can there be a mirror A?
Okay, that's a very good question. If we find the mirror of A, okay, my drawing is not that perfect, but this path should coincide this one. A had very good question. These two will have the same length, both shortest.
Okay.
Very good point. Either we move from A to B, or we move from B to A, we aim at the image point. Okay, a slightly different setting. Suppose we have a river. Okay, so this represents a river. And we are riding a horse. We want to move from one point to another point on the same side of the river. But we have the horse needs to drink water. Okay, needs to stop and somewhere to get some drink. How do we find the shortest way, the quickest way to move from A to B or riding the horse?
Does mirror work on this one?
Okay, yes, mirror also works on this one. So how do you find the shortest path?
Just do a mirror on the B.
Okay, so we can do a mirror B, and we connect this. Okay. Okay, so this point is when we let our horse get some water from the river. Okay, very good application. Okay. Okay. Next, we will introduce a new shape, and you have seen this in your homework. It's called parallelogram. Okay, it's a very long word. A parallelogram consists of two pairs of parallel sides. One pair, second pair. So these two lines are parallel. Label this A, B, C, D. A, B, B, C, D. And A, D, parallel, B, C. A very simple observation. for a parallelogram. We will use the following symbol for short. Then the pair of sides have the same length. Okay, let's think about this. Why? The two sides parallel, and the two sides parallel. Why? They must have same length. Why? They must have same length. We know it is true, but we also want to know why. Where do we start? Amy, what would you do? Any thoughts? We learned a lot of theorems about the triangles, but there's no triangle yet. We do get some triangles to get everything started.
I mean, you could bisect it.
Okay. So we could, one way we can connect B and D if we connect them. Okay. Now it creates two triangles. ABD, CDB. Okay. For convenience, later we will call this a diagonal of the parallelogram. Now we have triangles, and we know a lot of triangles. Let's try to use our knowledge on triangles. Go A, B, D, C, D, B. Are they congruent? Okay, some say yes. Okay, Amy, you said yes. Why? How do you justify this?
Because you said that AB is equal to CD and AD is equal to BC. So that means like all three of their sides are like equal.
Okay, so you apply this side theorem. The potential issue here is what we know and what we want to prove. In this theorem, what do we know? And what I want to prove, I'm proving. So here we wanted to prove these two have the same length. We want to prove these two have the same length. If we have proved this, then we can say, okay, side theorem. but we cannot use what we wanted to prove for the intermediate step. Do you agree with me? Okay, yeah. So this is close related to the problem on our homework, but it's slightly different in different directions. In our homework, we assume they have the same lines, then we prove they are parallel. Now we go the other direction. That's the homework, but now we go this direction. Okay, Kira.
What are we really trying to, are we trying to prove that they're parallel, or are we trying to prove that these two are equal?
Okay, we are trying to prove these two have the same length, these two have the same length.
Okay.
That's our theorem. What we know is that they're parallel. How could we use this information? Two triangles. Okay, Kira. Okay. Still thinking. Okay. Fred, an idea, Fred? The two triangles A, B, D, C, D, B. Can we prove they are congruent? Okay, let me give you a hint. Let's try to shoot for the angle side angle theorem. For these two triangles, they share the same side, BD and DB. Okay. Because it's the same segment, just different directions. To apply this theorem, we need two pairs of angles the same measure. What are they and why? Okay, Kira.
It has to be the side between the angles. So it would be ADB and ADB equals CDB, and then ABD equals CBD.
Okay, so here we have to change the order. Let's check if these two angles have same measure and why. Okay, Kira.
Because the BC and AD are parallel, and
Because the two lines are parallel
they
for
share like the
this
same line.
for this transversal.
So
These
the
two
alternate angles are
yes. For two parallel lines, the alternate angles have the same measure. Okay, very nice. That's our first part. Because AD is parallel to BC, the corresponding alternate angles ADB and CBD same measure. Let me try to move it over there. Okay, somewhere else. Let's find the second pair of angles that have same measures so that we can apply the ASA theorem. Okay, who wants to try? Jessica, what do you think? we want to apply the angle side angle. We have a side BD and DB. We have one pair of angles. We need another pair of angles. We have to check this pair and this pair. Do they have the same measure? Why? Amy, what do you say?
So then that would prove that yeah, that proves that the triangles are congruent then.
Okay, so that's the next step. Here we wanted to see angle ABD. Angle CDB. We want to say they have the same measure, but what's the reason for this?
Because it's like the same thing that Kira said, but on like the other pair of alternate interior.
Okay, yes. So we used this one already. Then we have another information we haven't used yet. Because these two pairs, the two lines are parallel for this. Okay, my drawing is not that good. Two lines are transversal. These two angles, they are alternate angles with the parallel lines. Therefore, they have the same measures. Because AB parallel CD. Okay, now we have ASA, the two triangles, ABD, CDB are congruent. Once they are congruent, the corresponding sides have the same length. So AB corresponds to CD, and AD corresponds to ADBC, or correspond to BC. Corresponding sides have the same length. Okay. Aaron, questions?
Is there only ASA here?
What do you mean?
I mean, like there could be a SSS, right? Or
Yeah, so that's the problem. To prove the theorem, the only conditions we know are parallel sides. We don't know this yet. We wanted to prove it, but we cannot use this to prove itself, right?
oh,
So to prove this theorem, this is what we want. It's not what we have. What we have is the two sides parallel, two sides are parallel.
Oh.
Using this information only, we prove that they are the same length. You see the difference between this one and the homework. The homework, we assumed they have the same length, then we proved they are parallel. For that one, we use side, side, side theorem. We go the other way because the alternate angles are the same, the two lines are parallel. Alternate angles are the same, two lines are parallel. So in our homework, we go this way, and this theorem, we go the other way. So what is what we have and what we want? We have to distinguish them. Okay. Now we can put them together, combine the homework and the theorem. We have the following observation. Okay. So if we only have the first one, we cannot conclude the second one. We cannot. There's no such implication. If we only have the second one, we cannot conclude this one. But if we have two of them, then we have two of this. They come in pairs. The first pair and second pair. And these two are equivalent. Okay. Another property. Let's consider a parallelogram. Oh, make it slightly more general. A, B, C, D. Previously, we connected B, D. We also connect A, C. And we call them B, D, and AC, the two diagonals of the parallelogram. Oh, not enough space. Okay, a very useful theorem. The two diagonals of a parallelogram, they bisect each other. Okay, so it means it divides the other into equal lengths. If we did call this point O, then we have AO equals OC, BO equals OD. Okay, let's think about how do we justify this? Why the two must have equal length? Why these two must have equal length? What theorem would we apply? Any idea? Aaron, what do you think? Why they must have similar lengths? Why they must have similar lengths? Could we use any of the theorems about congruent triangles?
Maybe the SAS theorem then.
Okay, we could, but which S, which A, which S? What do we know? Keep in mind what do we know and what we want. We wanted to prove they have the same length. We don't know yet.
We have a triangle AOB and a triangle DOC.
AOB, DOC. How to prove there? Okay, let me write down and see how could we prove that AOB COD, are they congruent? Why? So we have three theorems: SAS, SSS, ASA. Which one could we apply?
Okay, either the SAS or the ASA. I'd stick with the ASA to be honest, but yeah.
Okay, okay. Okay, let's try to check conditions for ASA. Which side?
Let's see.
This triangle, this triangle. Which side have the same length?
A, B, and DC.
AB and DC,
Perhaps.
because it's a parallelogram. We just proved the two sides have the same length. Okay, now we have a
Perhaps.
side. A, B, C, D. Okay, now the two angles. Let me check. Amy, give me first pair of angles with same measures. These two triangles.
Angle O.
Angle O, there are a lot of angles. Which one is angle O? You mean angle this one?
Yeah.
Okay, we could have angle AOB, angle COD. Is this helpful for the SAS ASA theorem? We have this side. If we pick this angle, they are opposite to each other, not the neighboring angles. Okay, think about this. Kira, what would you do? Any idea?
If we're using ASA, then not really.
Okay, let me give you the angle and ask you why they have the same measure. I see angle BAO, angle DCO.
I knew it.
Okay, Aaron, yes.
So wait. I was gonna say BOA, but yeah, I guess that works too. But yeah.
What do you mean?
I was gonna say that same angle, but in a different way.
Mean which one?
BOA.
BOA again, it will be this angle. But we only know this side and this side, they have the same measure. So this angle is not helpful if we apply the ASA.
Oh, I see.
Because we have picked these two sides. Amy, any updates?
I feel like I would use SAS.
If we want to apply SAS, which side are you picking?
Sides A, B, and AO.
AB and AO. So we know AB is CD, but do we know AO and OC? That's what we want, not what we have, right?
Yeah.
Okay. So the reason that we cannot apply this SAS for these two triangles, because the two sides, what we want, not what we have. These two sides, again, what we want, not what we have. Okay, so why these two angles, BAO, these two angles have the same measure? It's because these two angles are the alternate angles. These two lines with the transversal. Two lines are parallel, so the alternate angles have the same measure. Okay, so this because AB parallel CD. Okay, we can find the second pair of angles with the same measure. Aaron and
What?
so to apply the theorem, we need another pair of angles with the same measure. Okay, let me draw this. These two angles. Do they have the same measure?
Which one?
This one and this one.
Yeah.
Why?
Well, they're they're on opposite sides, right?
Mm-hmm.
Forget what's it called.
Alternate.
Yeah, alternate, yes. Alternate.
They are the alternate angles of these two lines, a different transversal. So this A, B.
So that means if angle D equals angle B, then angle A could equal C, because they're also alternate angles.
Well, so because we have so many lines, the angle A, angle C, the ambiguity, we are not sure which one you are talking about. So we have to use the 3 points. Angle A, B, O. Angle C, D, O. Okay, now let's check. Triangle, triangle, angle, side, angle theorem. It implies the two triangles. These two triangles are congruent. The corresponding sides have the same measure. AO, OC, BO, OD. In this way, we conclude O is the center point of AC and center point of BD. So the two diagonals, they bisect each other. In particular, we will call this the center of the parallelogram.
Is that why it's so important?
Yes. This is a very important point for the parallelogram. So the intersection two diagonals of a parallelogram is called center point. Sometimes we just call the center. So this diagonal O is the center. This diagonal O is the center. It's the center of both diagonals. We call it the center of the parallelogram. Okay. Any question about this one? Okay, as you can see, the properties of these parallelograms is all followed from the theorems we learned about the triangles. In the future, we'll learn quite a few similar results. We use properties of triangles to get the properties for more general geometric shapes. Okay, we will stop here today, and there'll be homework, and we'll see you next week. Any questions?
Is the homework gonna be based on this?
They'll be closely related.
All right.